Now it's time to see why bigger AI models suddenly become smarter. In fact, I have a personal experience with this. When ChatGPT started, ChatGPT became a thing around September 2022. And, I got wind of it. I mean, I was just hearing about it faintly, for all the while. But around January, February 2023, I began to just experiment with it. And I mean, as a mathematics person, right, I gave it, sometimes I would say, I'll ask a question like, what is 18 combination 3? I already know the answer, right? But ChatGPT will end up giving a very wrong answer. And I'll be like, oh, this is not the correct answer. And, within the space of 6 months, all of that became a thing of the past. And ChatGPT now began to give more accurate results and everything. So this is what, what the process of that is what this video is here to address. Why bigger AI models suddenly become smarter. And of course, the simple answer would be surrounding the idea of scaling laws and emergent abilities. So these are your answers up front. I'm giving you the answers up front, but then let's go into the details. By the end of this lesson, you should be able to explain why larger AI models usually perform better and understand the meaning of AI scaling. You state the three major scaling dimensions, understand AI scaling laws, apply simple scaling law equations, and explain emergent abilities, understand why frontier models are so large, and simulate scaling behavior using Python. So let's go ahead and look at this. So in the introduction, one of the greatest discoveries in modern artificial intelligence is surprisingly simple, right? So making models larger often makes them significantly smarter, right? So this observation, so it's more like the more data you have, the better your system is going to perform. So this observation changed the entire AI industry. So for many years, researchers believed that improving algorithms was the primary way to build better AI systems. However, recent evidence has shown that simply increasing three quantities simultaneously, like the model size, the training data, and the computational power, can dramatically improve performance beyond just the algorithm. So, even more surprisingly, some abilities do not improve gradually. They appear suddenly once the model becomes sufficiently large. So, this lesson explores two of the most important discoveries behind modern AI. Those are the ideas of scaling laws and emergent ability. So, these ideas explain why today's frontier AI systems are trained using hundreds of billions of parameters and enormous computational resources. So, once you have sufficient data and good computational power, and a nice model size, you're good to go, even without bothering so much about the algorithm. Now, question, what does scaling mean? Because, we're talking about scaling laws and emergent abilities. Now, what does scaling mean then? So, scaling simply means increasing the size of an AI system, basically. So, researchers usually scale one or more of the following. You can scale the number of parameters, you can scale the amount of training data, or you can scale the computational resources. So as these quantities increase together, the intelligence of the model generally improves. And this process is known as AI scaling. So parameter, training data, and computational power, basically. So the three dimensions of scaling now, that's all okay. Yeah, the three dimensions of scaling. Modern language models improve by scaling three important quantities. First, we have the model size. So the number of trainable parameters, that's what the model size addresses, just like what we have there as training data, right? So the modern language models improve by increasing three important quantities. Model size is number one. The number of trainable parameters. Examples include you can have 10 million parameters, 100 million parameters, 1 billion parameters, 100 billion parameters. Larger models have more capacity to learn complex patterns because they are trained on bigger parameters. So talking about training data now, the amount of text, images, or other information used during training. Examples include millions of tokens. You can have billions of tokens or trillions of tokens. Then more data exposes the model to more concepts and situations like that. Then you have compute. So we talk about the model. Model relates to parameters. Then you have the training data, which relates to tokens, and then we have the compute. That the compute is talks about the computational resources used during training. So examples include GPU, that's graphics processing units, and TPUs. You have flops also, floating point operations. So more computation allows the model to learn more thoroughly from the data. So the better you can compute, the better it will be easy for the model to learn. Then why do we need all these three? So talking about the model size, the training data, and of course the compute. Now, why do we need all these three? Imagine trying to educate a student. A larger brain alone is not enough. A student with a larger brain does not guarantee anything, right? But the student also needs the books, teachers, and practice time, right? So books are like the um they are the tokens, kind of. They are the token. They are akin to tokens. Teachers are like the model size, the model, and practice time can talk about compute. Likewise, an AI model needs enough parameters, enough data, and enough computation. So removing any of this limits overall performance. So we need parameters, we need the data, and we need computation. Modern AI therefore scales all three simultaneously. So it scales model size, compute, and of course, training data simultaneously to become very powerful. Now, and talking about an analogy now, building a library, think of training an AI model as building library. First of all, the parameters will be the size of the building, more like how many rooms, how many shelves, and things like that, how many floors. If it's more than a ground floor building, then those are the parameters now. Then training data now will now be the number of books, right? Then the compute is the amount of time librarians spend organizing everything. That'll be like how that's like building a library right there. So it's about the same thing as training an AI model. So a huge library, which with only 10 books, is not very useful. So you have a big library and there are only 10 books. Makes no sense. Likewise, millions of books stored inside a tiny room become overcrowded also. So good performance requires balancing among all three resources. You have the size of the building is good enough, and the number of books they are not too few and they are not too many, and then they compute the amount of time librarians spend organizing everything. So if you have more librarians organizing, it's faster to set up the library. If you have fewer librarians, it is slower, like that. So good performance requires balancing among all three resources: model size, training data, and of course the compute. Now let's talk about a historical trend. Early neural networks contained only a few thousands of parameters. So as computing power increased, researchers built larger models. So approximate progression now. In the 1990s, the typical model size contained thousands of parameters. In the 2000s, we had millions of parameters. In the 2010s, we had hundreds of parameters. In the early 2020s, of course, in 2022, the whole generative AI thing started. So we have tens to hundreds of billions, and that's why you can see generating the models we have now are so efficient. Then we have frontier models that are even larger, right? Like all the ChatGPTs of this world, the Gemini, the close of this world. So the rapid increase in scale has been accompanied by remarkable improvements in capability. So that rapid increase has been accompanied by remarkable improvements in capability. Now the next thing we talk about scaling laws, right? Scaling laws are mathematical relationships. I mean, scaling laws reminds me of power law, which is also related, yeah. So scaling laws are mathematical relationships describing how model performance changes as the model becomes larger, right? So they are mathematical relationships describing how model performance changes as the model becomes larger. Instead of improving randomly, AI performance follows surprisingly predictable patterns. So researchers discover that the prediction error often decreases according to a power law. So a simplified scaling law is L of n equals an raised by minus alpha plus b, where ln is the loss, which is the function of the model size n, a is a positive constant, alpha is the scaling exponent, while b is the irreducible minimum loss. So that is, if whatever happens, the b is the minimum loss, like that. So that's a simplified scaling law right there. Like we said, the researchers discovered that the prediction error often decreases according to a power law. So this n raised by minus alpha talks about is the summary of the power law idea. So understanding the formula itself now, the equation L of n equals an raised by minus alpha plus b contains several important ideas as n. So as n increases, n raised by minus alpha becomes smaller, because the bigger this is, the smaller n raised by minus alpha becomes, because that's a negative power. Therefore, L of n decreases overall as the model size becomes bigger and bigger. Then a lower loss means the model makes fewer mistakes. So of course the goal is as the model becomes bigger, the loss should be smaller. That makes serious sense. That means that as the model size increases, the loss should become smaller, resulting to fewer mistakes. Consequently, larger models generally produce more accurate predictions. Now, we then talk about interpretation of each quantity now. N represents model size, usually measured by the number of parameters. So model size is measured by parameters. Then, we have model size by modeled by parameters. You have the training data, which is about tokens, and then you have the compute power, right? So it depends on GPUs or whatever you're using. Then alpha controls how rapidly performance improves. So as alpha is getting bigger, the loss is the loss is becoming smaller. So larger values of alpha correspond to faster improvements in the model. Then B represent the lowest achievable loss. So even infinitely large models cannot reduce the loss below this value because of noise and uncertainty in the data. So let's assume that this becomes infinity. So it means you have n raised per minus infinity. That's n over infinity, which is so everything basically goes to zero. So, but whatever happens, you cannot get a model without some loss. So that's why B is the baseline loss in a way. So even infinitely large models cannot reduce the loss below this value because of noise and uncertainty in the data. Now, why is this important? Scaling laws provide a roadmap for AI development. So instead of guessing whether a larger model will perform better, researchers can estimate the expected accuracy of a model, the expected loss, the required computes, the required data, and future improvements. This helps organizations decide whether building a larger model is worth the enormous computational cost. So it's more like doing a kind of cost benefit analysis, like how much. So if you don't have to, if you have a particular model, right, and you are thinking of increasing the model size, I increasing the model size may not reduce the loss significantly. So at the end of the day, it may not really be worth it. So you want to be sure that increasing the model size is going to be worth it at the end of the day. That's basically what that is for. Now, suppose the scaling law is given by L of n equals 2 n raised per minus 0.4 plus 0.1. So find the expected loss when n is 100. So when n is 100, you can just substitute 100 for n. So you have L of 100, that's 2 into 100 raised per minus 0.4 plus 0.1. That's like 100 raised per minus 4 over 10. That's 2 over 5. I mean, we can do all of that. So since 100 is 10 raised per 2, right? 10 raised per minus 0.4 is like 10 raised per 2 raised per minus 0.4, which is 10 raised per minus 0.8. That's approximately 0.1585. So you then have 2 times 0.1585 plus 0.1. So the baseline loss is 0.1. So everything together is 0.417. So the expected loss uh, for a model whose size is 100 is approximately 0.417. So that's our example one right there. For example two, imagine you now increase the model size again. Now suppose the model becomes much larger. Instead of the 100 we had before, it's now 100 times, like you square that. So now suppose the model becomes much larger. Let n be 10,000, and that's 100 times 100. Compute the expected loss. Now using L of n equals to 2n raised per minus 0.4 plus 0.1, we obtain L of 10,000 to be 2 into 10,000 raised per minus 0.4 plus 0.1. Since 10,000 is 10 raised per 4, then 10,000 raised per minus 0.4 is 10 raised per minus 1.6, because this is basically 10 raised power 4. So that's 4 times minus 0.4, that's minus 1.6, and that's approximately 0.0251. Hence, L of 10,000 is now 2 into 0.0251 plus 0.1, which is 0.150402. The other time we had 0.417 as loss. Now it's 0.1502. So you can see the difference is not so large. This is approximately to two decimal places, that's 0.42 here. Now this is to two decimal places, that's 0.15, 0.42. Oh yeah, it's sorry, it's different. That's 0.417. This is 0.15. So that's significant. Notice that increasing the model size by a factor of 100 substantially reduces the prediction error. Yeah, I mean that is 0.417. This is 0.150. I was thinking in terms of 0.15 and 0.14. No, it's 0.4 up there and 0.15. So that's significant. So example, now if you compare two models, suppose two language models have the following losses. Model A has loss 0.38. Model B has loss 0.21. Which model performs better? Of course, the one with the, well, we can't be sure. I mean, from the face value, right? The smaller loss means better model for sure. So solution, lower loss indicates fewer prediction errors. So 0.21 is less than 0.38. So in that case, model B performs better for sure. Just going by the loss. So this illustrates why researchers aim to reduce the loss during training. So that's why loss is the big deal. Want to reduce that as much as possible. Yeah. And that is why we do the whole back propagation thing. So visualizing a scaling law now. Of course, from what we see already, as the model gets bigger and bigger, the scaling becomes the loss becomes smaller and smaller. So you see, for model size 10 raised power 2, you have loss above 0.40. Then at 10 raised power 3, the loss is now like between that's like 0.225 or something like that. Yeah, 0.225 roughly. And at 10 raised power 4, it's 0.15. At 10 raised power 5, it's something like 0.155 or something like that. And then as it's getting bigger, the loss is reducing drastically. So this graph shows that the loss decreases rapidly at first and then gradually approaches a minimum value. Now the question is, why does improvement slow down? Scaling laws do not imply unlimited improvement, for sure. So initially, small increases in model size produce significant gains. So as models become larger, each additional increase produces a smaller improvement. So this phenomenon is known as diminishing returns. Of course, there's a lot of diminishing returns in economics. We have it here too. So it gets to a point where increasing the model size doesn't make so much difference. So mathematically, the power law curve gradually flattens as n approaches infinity. So as you can see here, as the model parameter or the model size is getting bigger and bigger, the loss is getting, so it's the drop in loss is slowing down, and at some point it doesn't make so much sense to increase the model anymore. So consequently, large models continue to improve, but the improvement becomes increasingly expensive. And then you have to be then sure that you want to keep improving because I mean at some point they don't make so much difference anymore. Now, talking about scaling data now, model size is not the only quantity that matters. We talked about model size, that's L of n, uh, a n raised power minus alpha plus b. But we can talk about scaling data too. Model size is not the only quantity that matters. Training data also follows a scaling law. So a simplified relationship is L of D equals CD raised by minus infinity minus beta plus E, where D is the amount of training data, C is a constant, beta is the data scaling exponent, E is the minimum achievable loss. So increasing the amount of high quality training data generally reduces prediction error. So training data can also follow the scaling law apart from just like model size. Now, suppose L of D is 4D raised by minus 0.5 plus 0.2. So find the loss when D is 400. That is, the training data uh, is 400. Yeah, that's the amount of training data is 400. So substitute into the formula, you have 4 into 400 raised by minus 0.5 plus 0.2. So 4 raised by minus 0.5 is like 1 over, that's 4 raised per minus half. That's 1 over 400 raised per half. That's 1 over square root of 400, which is 1 over 20, and that's 0.05. And then we obtain L of 400 to be 4 into 0.05 plus 0.2. So 4 times 0.05 is 0.2 plus 0.2, that's 0.4. So in that case, the loss is 0.4 when you have just 400 training data. But then, um, okay, yeah, that's for training data. We can also we can also scale the compute power. So training, so we've seen that what makes bigger AI models suddenly become better is about model size, which depends on the parameters, the training data, which depends on the tokens, and then the compute power. And all of them, the scaling law can apply to all of them. So scaling compute now, training computation also influences modern quality, right? So a simplified compute scaling law is also, so it's basically the same thing. L of C equals F C raised by minus gamma plus G. So where C represents computational resources, F and G are constants, then gamma is the compute scaling exponent. So increasing computational resources generally allows the optimizer to learn better representations from the data. So you have a general idea here. So whether you're talking about, let me say this now. So whether you're talking about model size So model size, or you're talking about training data, training data, or you're talking about compute, or if you like, call it computational resources. All of them together can follow the scaling law, which says that loss as a function of any of them. So let's use a generic thing to represent each of them now. So let's say loss as a function of whether you like M, T, or C is basically any constant. Let's say you have a constant A multiplied by any of them. So whether it's MTC raised power minus whatever, say alpha, then plus B here. So that law applies if you like M or T or C separately. So simply L of M will be A M raised power minus alpha plus B. Then L of T, that's training data, that is still A T raised power minus alpha plus B. I mean, if you change the parameter, it doesn't change anything as far as the meaning is preserved. So you have A C raised power minus alpha plus B. So that can apply to these three things that affect the performance of of models like that. So let's talk about the relationship between the three scaling dimensions now. Modern AI systems improve by increasing model parameters, training data, and computation. So these quantities work together. So a large model trained on very little data will underperform for sure. Likewise, an enormous data set trained using a tiny model cannot fully capture the underlying pattern. So successful frontier models carefully balance all three scaling dimensions, talking about model parameters, training data, and computation. Now, let's talk about compute optimal scaling. Suppose you have a fixed computational budget. Say, of course, you can only have so much, depending on your budget. So suppose you have a fixed computational budget, should you build an extremely large model with little data or a moderately large model with much more data? So research has shown that there's an optimal balance. So there should be a balance between compute and optimal scaling. So too many parameters waste capacity, too little data causes under training, too much data with a very small model limits what the model can learn. And then the best performance is achieved by balancing the number of parameters with the data you have and the compute. So this idea is called compute optimal scaling. So that tuning the number of parameters you have, talking about the model size, and then the training data, talking about the tokens, and then the compute. Tuning it to get the best kind of model is what to get the optimal balance, right? Is what is called the compute optimal scaling. So we've been talking about scaling all along, and we just like we said from the beginning, that it took concepts that makes bigger AI models to suddenly perform excellently about scaling and emergent abilities. And we've seen scaling, and we've seen that we can scale a model by tuning, by adjusting the model size, the the model size, the training data, and the compute power, the compute or the computational resources, if you like. Now let's talk about emergent abilities. One of the most surprising discoveries in modern AI is that some capabilities do not improve gradually. Instead, they appear suddenly once a model becomes sufficiently large. So it looks like once you achieve that computational optimal scaling like this, you can expect the model to, just perform so drastically. So they appear suddenly once a model becomes sufficiently large. These two capabilities are called emergent abilities. So an emergent ability is a skill that is absent in smaller models. It appears unexpectedly in larger models and was not explicitly programmed by humans. So that's why it is emergent abilities, right? So when the model is small, you don't see them. Then appears unexpectedly once you hit a particular threshold in a large model, and it's nothing, it has nothing to do with human capacity, what any human has programmed. So this phenomenon has become one of the defining characteristics of today's frontier AI models. Now, why are they called emergent, right? Of course, your guess is as good as mine. The word emerge means to appear unexpectedly from the interaction of many simpler components. For example, individual water molecules do not possess the property of a wave. However, millions of water molecules together produce ocean waves. Similarly, a single neuron inside a neural network cannot reason. Yet, billions of interconnected artificial neurons working together can exhibit sophisticated reasoning abilities. So let's look at an everyday analogy. Imagine learning to play the piano. During the first few weeks, a student can only play individual notes. After months of practice, they begin to play complete melodies. Eventually, they can improvise music without memorizing every note. Improvisation is an emergent skill. Like you just start, just see yourself playing the piano without thinking, without really thinking, so to speak. So it appears only after sufficient knowledge and experience have accumulated. So large language models behave in a similar way. So, examples of emergent abilities now. Researchers have observed that sufficiently large language models can suddenly perform tasks such as logical reasoning, mathematical problem solving. I told you my experience with ChatGPT initially, right? So when I will say, what is the solution to 16 combination 3? And then it gives me a wrong answer. And then I'll have to tell it the correct answer. And then we argue, we keep having a back and forth until then it now gets it right. But today, if you just try 16 combination 3, you can be sure you're going to get a perfect answer from ChatGPT because over time the model has become so large and it can suddenly perform tasks such as logical reasoning, mathematical problem solving, code generation. Initially, there were more bugs in the codes generated by AI, but these days you can get perfect codes, just in one, just with one prompt without that you don't have to even debug, depending on what you're doing. So it has also helped language translation, summarization, question answering, planning, scientific writing, tool usage, in context, in context learning rather, and multi-step reasoning. Many of these capabilities are weak or completely absent in much smaller models. So we then have small models versus large models now. Consider three hypothetical language models. Let's say one is a small one, which predicts the next word reasonably well, and you have a medium one, which writes coherent paragraphs and answers simple questions, and you have a large one, which reasons, plans, writes code, solves mathematics, and follows complex instructions. Although the increase in size is gradual, the improvement in capability may appear sudden. So this sudden qualitative change is the hallmark of emergence. So they are more like what some people call unintended consequences. Then we have phase transition analogy. Of course, there's this. I did a bit of engineering, and in heating and all of that, you have the idea of phase transition. So emergent abilities are often compared with phase transition in physics. Consider water. Below 0 degrees, water is solid ice. Above 0 degrees, it suddenly becomes liquid. Now, the interesting thing is that at 0 degrees, when it is solid ice, once you start applying heat, at first it feels like the heat is not achieving anything. The water remains at 0 degrees. All of a sudden, it becomes liquid, and then the temperature starts increasing, and it becomes liquid, right? And you keep applying heat, and then it gets to 100 degrees. And as you keep applying heat at 100 degrees, it seems nothing is changing. All of a sudden, you discover that the water is becoming gas. So it suddenly becomes liquid, and above 100 degrees, it becomes steam. So the molecules have not changed, only the scale of their collective behavior has changed. Similarly, large AI models may cross certain thresholds where entirely new behaviors become possible. And that is why people are afraid that hope we won't get to a point where AI becomes the AI hijacks the whole process themselves and build and begin to control things by themselves. So that's one fear people really have about AI. Now, why does emergence happen, right? Researchers are still investigating the exact reasons. Several hypotheses have been proposed, like richer representations. Larger models can represent increasingly complex concepts and better pattern recognition. More parameters allow the model to recognize subtle statistical relationships. Then you have higher dimensional features. Larger hidden layers create richer internal feature spaces. Then you have better memory. More parameters allow the network to store far more knowledge acquired during training. Large transformer models learn increasingly sophisticated attention patterns that improve reasoning across long texts. So these are possible reasons why emergence may happen. Richer representations, better pattern recognition, higher dimensional features, and then better memory and better attention. Then let's talk about internal representations now. During training, a transformer gradually develops internal representations of the world. Instead of memorizing isolated words, it begins to organize concepts hierarchically. For example, rather than simply recognizing the word dog, a large model may internally connect it to mammals, pets, animals, loyalty, barking, veterinary medicine, biology, and domestic life. Different context and nuanced uh, environment for the word dog. So this richer representation supports more advanced reasoning. Then let's talk about feature hierarchies. Neural networks learn increasingly abstract features. For example, early layers may recognize letters, punctuation, simple words. Middle layers may recognize phrases, grammar, and syntax, while later layers may recognize concepts, reasoning patterns, relationships, and word knowledge. So larger models develop deeper and richer hierarchies than smaller models. Now let's talk about emergence not being a magic. So basically, emergence is not magic. So imagine abilities do not imply that the model has become conscious, not at all. Yeah, this is what I was trying to talk about the other time. So people are afraid that maybe one day AI will become conscious and then hijack the process from humans, and they can now maybe drive the world to the end or something like that. So emergent abilities do not imply that the model has become conscious. Instead, the behavior results from learning statistical regularities, richer internal representations, larger computational capacity, and improved optimization, extensive training data, and of course, from extensive training data too. So the appearance of new skills reflects the complexity of the learned representations rather than human-like awareness. So it's not about consciousness or awareness. It's about, you know, learning statistical regularities, richer internal representation, larger computational capacity, improved optimization, and extensive training data. Now let's talk about in-context learning. So one remarkable emergent ability of large language models is in-context learning. Instead of updating its parameters during use, a large model can often learn a new task simply by reading examples provided in the prompt. So the model identifies the pattern and applies it to new inputs without additional training. So this ability becomes much stronger as model size increases. So, example four now, in context learning. Uh, so an example about in context learning. Suppose we provide the following examples of a language model. So English to French translation. So you have dog, which is chien. You have cat, which is cha. So bird now, although the model has not been retrained, it recognizes the translation patterns and predicts. So even if it had not come across the word the French word for bird before, it already says, oh, okay, maybe it knows the French word for bird, and you have not told it explicitly that, okay, uh, bird, the word is there, right? So there's a French English thing already in the mix, but without even being retrained, right? So it already knows that get the English word and supply the French word. Get the English word for dog, it provides chi, and get cat, it provides cha. So from that, it can learn that, oh, bird automatically has to be oiseau. So this illustrates in context learning. So the model temporarily learns from the examples contained within the prompt itself. Now, there's the idea of chain of thought reasoning. Another important emergent ability is chain of thought reasoning. So we are talking about the abilities of emergent learning now. That's in context learning, and then we saw the example of in context learning. So from your prompt, it can even learn what to do. Then you have chain of thought reasoning. Another important emergent ability is chain of thought reasoning. Instead of producing an immediate answer, the model generates intermediate reasoning steps before arriving at the final solution. And that is why sometimes you say, "Oh, I need a program to do this, blah, blah, blah." And then, so instead of giving you the code directly, the AI tells you, okay, for more context, can you supply, do you have, what is what? So it asks some clarifying questions so that by the time you answer the questions, it gives you something more suitable. So breaking a difficult problem into smaller logical steps often improves accuracy on tasks involving mathematics, logical reasoning, planning, and scientific problem solving. So, an example on chain of thought. Consider the problem. A bookstore sells a notebook for $8 and Sarah buys six notebooks. How much does she pay? So, a reasoning process is step one, price per notebook. You have $8. Then, step two, number purchased. You have six. Then, you need to multiply, and that's 8 times 6, that's 48. Therefore, Sarah pays $48. So, large language models generally perform better on multi-step reasoning tasks than much smaller models like that. So, we have a Python simulation of emergent behavior now. So you have a kind of sigmoid function. So learning starts slowly and then it takes off at some point and goes so rapidly and saturates. So that's so as the model scale increases, the capability score, goes on like that from zero and it stays there a bit, keeps learning, and all. So this is like very. looking so much like you still have small models, and then it crosses this 40 threshold or whatever threshold you may set, and then it just jumps and starts behaving, start performing so excellently, and then it also reaches a saturation point. As we know, that it gets to a point that increasing the model size makes no huge difference anymore. So the curve remains relatively flat for small models and then increases rapidly once a critical scale is reached, illustrating the idea of an emergent capability. So interpreting the emergence curve now, you see this sigmoid. When we say a sigmoid function is this kind of saturation thing. So it's you can use it to describe chemical reactions, or even eating. So when you start eating, you derive. So maybe you're very hungry. So you take the first spoon of whatever you're eating, and then it keeps going. Then it crosses the threshold. You enjoy it so much, and then it gets to a point. Even when you still have enough food, you still have more food, but you cannot eat, or you don't derive any more satisfaction from it. That's although it's not that diminishing return, it's more like you reach a saturation where you cannot have any more. So interpreting the emergence curve, the segment shaped curve illustrate three phases. You have phase one, which this phase one now, which corresponds to small models, like I said the other time. So performance improves slowly, and many advanced tasks cannot be yet solved. But then you go to phase two, that you reach a critical threshold where capability, you have a critical threshold and capability increases like rapidly, and new reasoning abilities begin to appear. So in this process, you have new things, emergent behaviors coming on, and then of course the final stages for very large models which performance continues improving but eventually begins to level off. So this simplified illustration captures the qualitative behavior observed in many language models. So you see phase two starts from somewhere around here, and then it begins to increase, and phase three is more increase, and then leading to some saturation where you have a leveling off like that. So this simplified illustration captures the qualitative behavior observed in many large language models. So now, why are frontier models so large? So when we talk about frontier model, we are talking about things like GPT, maybe GPT-4 or Fable, that is the biggest one now from Claude and all that. So today's frontier AI systems are intentionally built at enormous scale because larger models consistently demonstrate stronger performance. Increasing scale generally improves reasoning, mathematics, programming, multilingual understanding, scientific knowledge, planning, instruction following, document summarization, tool use, conversational ability. These improvements motivate the substantial investment required to train frontier models. So now the question is, what are frontier models, right? I gave some examples. A frontier model is among the most capable AI systems available at a particular point in time. At this point, okay, let's do a simple search of current frontier models, current frontier AI models, AI models. Okay, so current frontier AI models are led by flagship offerings from major labs, including Anthropic's Claude Opus 5, OpenAI's GPT 5.6 Sol, and Google's Gemini 3.5 Flash. So basically, Opus 5, GPT 5.6 Sol, and of course, 3.5 Flash from Gemini. So these are like the big boys, so to speak, you know. Yeah, like that. So a frontier model is among the most capable AI systems available. So you can see these are the three companies at the forefront of AI. You have OpenAI that came up with the whole idea of ChatGPT. Then you have Anthropic that gave us Claude, and you have Google that gave us Gemini. Of course, you have other ones like is it SpaceX? Should we call that SpaceX now? Yeah, Elon Musk's X. So a frontier model. A Grok, right? Grok came from Elon Musk. So a frontier model is among the most capable AI systems available at a particular point in time. Such models are characterized by extremely large parameter counts, training on massive data sets, advanced transformer architectures, extensive computational resources, strong performance across a wide variety of tasks. So frontier models represent the current state of the art in artificial intelligence. So then we talk about characteristics of frontier models. Most frontier models possess several important features. So you have long context understanding, multimodal processing, strong reasoning ability, strong code generation, mathematical problem solving, scientific writing, tool integration, planning, dialogue. I mean, you can have a conversation with most of these tools these days. Sensible dialogue for that matter. I mean, sometimes I engage some of these AIs in, like a kind of reasoning, trying to, bounce my ideas off AI, and it's always a very fruitful experience. Then you have retrieval capabilities. These capabilities are made possible by advances in scaling, optimization, and training methodology. So imagine comparing different scaling exponents now. So we have, let's say we have models with model sizes 2,6,200, and we have the exponent 0.2, 0.4, 0.6, and we have the loss now, n of minus alpha, n raised per minus alpha. Basically we're talking about the whole scaling thing, which is about the power law. So effect of the scaling exponent. So if alpha is 0.2, so as the model size increases, so for alpha 0.2, so the loss reduces not as fast as the orange one. The green one it has the loss decreasing the fastest, because of the power, the power, uh, the exponent there. So larger values of the scaling exponent produce a steeper decrease in loss, indicating faster improvements as model size increases. So as model size increases, you have faster decrease in loss for sure. And that is the idea. So limitations of scaling now. Although scaling has produced remarkable advances, simply building larger models is not a complete solution. Like we said already, simply building larger models as models become larger and larger, it gets to a point that there's no use for having a larger model. So important limitations include extremely high computational cost, large energy consumption. Of course, there's this story about, every prompt, every day, saying telling an AI that telling an AI that you love it, it's using a lot of water somewhere in one data center. So that kind of thing. So you can have large energy consumption, expensive hardware requirements, long training times, diminishing performance gains, and environmental impact, increased deployment cost, and safety and alignment challenges. So future AI research therefore focuses not only on larger models, but also on making them more efficient, reliable, and trustworthy. So you have applications of scaling laws now. So scaling laws have transformed the design of modern artificial intelligence. So rather than relying on trial and error, researchers use scaling laws to predict how performance will improve as model size, training data, and computational resources increase. Right? So some important applications include designing large language models, estimating computational requirements, selecting appropriate model sizes, determining computational data sets, planning training budgets, forecasting future model performance, and comparing competing model architectures, optimizing resource allocation. So scaling laws provide a scientific framework for building increasingly capable AI systems. So like that. And then we also have applications of emergent abilities. Emergent abilities enable AI systems to perform tasks that smaller models cannot accomplish reliably. Examples include multi-step mathematical reasoning, software development, scientific literature analysis, document summarization, multilingual translation, legal document drafting, medical question answering, educational tutoring, intelligent. I mean, I use a lot of AI in my educational tutoring process for sure. So autonomous agents, these applications become increasingly effective as model capabilities improve. Then we talk about case study, why scaling changed AI now. Before the discovery of scaling laws, researchers primarily focused on designing increasingly sophisticated algorithms. Modern AI research revealed a different strategy. Instead of constantly inventing new architectures, remarkable improvements could only be achieved by increasing model size, training data, and increasing computational resources. So this insight fundamentally changed the direction of AI research and accelerated the development of today's frontier models. So focusing on these three can cause a lot of advantage. So comparing small and large models now. So talking about feature for small model and frontier model. So for the parameters, we have millions of parameters for small model, and we have billions or more for frontier models. For knowledge capacity is limited, very large for frontier. For small model, the context understanding is short, but it is long for frontier model. For reasoning, it's basic reasoning for small model, advanced reasoning for frontier model, then limited coding capacity for small, and strong coding capacity for frontier. Simple mathematics can be done by small models, while multi-step models Multi-step mathematics can be done by frontier models. Translation, moderate translation can be done by small models, while high-quality translation can be done by frontier models. Limited for scientific writing, small model that is. Frontier model is strong for scientific writing. Then small model is minimal. There's minimal to use and advanced to use for frontier model. Then lower generalization for small model and higher generalization for frontier. So although larger models generally perform better, they also require substantially greater computational resources. So our key takeaway so far, the major ideas from this lesson are scaling means increasing model size, data, and computation. Then AI performance often follows predictable power laws. So larger models generally achieve lower prediction error. Increasing only one scaling dimension is usually insufficient. So you need to increase not just model size or not just data, training data, not just computation. You should increase model size, training data, and compute simultaneously. So emergent abilities are new capabilities that appear once a model becomes sufficiently large. So frontier models combine enormous parameter counts, massive data sets, and extensive computation, thereby taking care of all the three areas. Scaling has become one of the central principles of modern artificial intelligence. So scaling simply follows power law. In summary, modern artificial intelligence has been transformed by two remarkable discoveries, scaling laws and emergent ability. So scaling laws show that model performance improves predictably as the amount of training data, model parameters, and computational resources increase. These relationships enable researchers to estimate future performance and design increasingly capable systems. Emergent abilities demonstrate that sufficiently large models can acquire entirely new capabilities that were absent in smaller models. So skills such as reasoning, coding, planning, translation, and in-context learning become increasingly reliable as model scale grows. Together, these discoveries explain why today's frontier AI models are trained with enormous computational resources and why scaling continues to play a central role in advancing artificial intelligence. So we have our glossary. So scaling is one word we've been using a lot, which simply means increasing one or more of the model size, training data, or computational resources. I mean, we know it's best to increase to tune all of them at the same time. Then you have a scaling, which is a mathematical relationship describing how model performance changes as scale increases. Then you have parameter, which this is the trainable numerical value within a neural network. Okay, maybe yeah, whatever. So if we talk about the a cat now, maybe you are working on an AI model that recognizes images. So maybe you want to talk about the texture, the edge, the corners, and things like that. Those may be parameters. Then training data, the examples used to teach a machine learning model. So of course, training data are things that humans have probably generated that you can feed to the model to now make it do its work in the future. Compute is simply talking about computational resources required for training, often measured in flops. Then loss is a numerical measure of prediction error. So lower loss indicates better performance. So loss is basically the difference between the real value and what the model gives. Then power law is a mathematical relationship in which one quantity changes as the power of another. Then uh, you have emergent ability, which is a capability that appears unexpectedly once a model exceeds a certain scale. You have frontier model, one of the most advanced AI models available at a given time. So it's not fixed. That's why it's at a given time. So currently, we know it is Opus 5, from OpenAI. It is GPT 5.6 Sol from, GPT 5.6 Sol from OpenAI. Uh, Opus 5 or even Fable, from Anthropic, that's the Claude people, and then of course you have Gemini and all that. So you also have the idea of in-context learning, the ability of a model to learn from examples contained within a prompt without updating its parameters. Then you have chain of thought reasoning, solving a problem through a sequence of intermediate reasoning steps before producing the final step. So that's more like a step-by-step approach to solving a problem in short. So now we come to our practice problems. So here we can, okay, let me just maximize this so you can see questions 1 and 2. I'll be solving two of these as I get to do. So let's see. Um, so solve two of these. I'm solving problems 1 and 20. So suppose the scaling law is L of n is 3n raised per minus 0.5 plus 0.2. Find the loss when n is 100. So we're going to do that. Then 2, a model follows the scaling law. Ln is 5n raised per minus 0.3 plus 0.2. And calculate the expected loss when n is 1000. So so I'm doing 1 and 20. So you can see questions 1 and 2 here. Then here you can see 3 and 4, all of 3 and 4 clearly. Of course, which model performs better? The one with this lower loss performs better. So model A performs better because the loss is 0.18, which is smaller than 0.27. It's smaller than 0.27. Then you have questions 5 to 8 here. You can see all of questions 5 to 8 here. Then you can see questions 9 to 12 here. Then you have 13 to 17, all of that here. Then you have 19 and 20. So another problem I'll be solving will be question 20, which says, suppose you have a fixed computational budget. Would you choose a very large model trained on a small data set or a moderately large model trained on a much larger data set? Justify your answer using the idea of compute optimal scaling. So we'll talk about that also. So let's go and take care of question 1 and then question 20. So let's go for problem 1. Okay, I think I like the bigger one. Okay, I can even pick something else. I can pick blue. So this is problem 1. Problem 1. The scaling law. So in that problem 1, the scaling law is L of n equals 3n raised per minus 0.5 plus 0.2, like that. So, and we are given n to be 100. So if you substitute the formula, right? Okay, let's see what I can change here. Yeah, so substituting, substituting. So we have L of 100 to be 3 into 100 raised per minus 0.5 plus 0.2. So that is 3 into 10 raised power 2. Minus 0.5 is minus half here, plus 0.2. So that means 2 cancels 2. So we have 3 into 10 raised power minus 1 plus 0.2. So that is 3. Okay, I mean, to make it more logical, so we have 3. 10 raised power minus 1 is 1 over 10 plus 0.2. So that is 3 over 10 plus 0.2, which is 0.3 plus 0.2. So that's L of 100. So we say that L of 100 is 0.5 easily. So in this case now, we can then conclude that. So a model with 100, a model with 100 parameters, a model with 100 parameters, in this case, not in every case, in this particular case, a model with 100 parameters is expected. This is a simplified case, so so you have to look at your context. So a model with 100 parameters is expected to have a prediction loss, a prediction loss, a prediction loss of 0.5 according to the given scaling law, according to the given scaling law. That goes. Then I come to problem 20. So for problem 20 now, so imagine, so it says suppose we have a fixed computational budget. Maybe you have a particular GPU and you don't have more than that. So suppose you have a fixed computational budget. Okay, should we choose? Should we choose? Should we choose one, a very large model, trained on a small data set, on a small data set, or a a moderately large model trained trained on a much larger data set. So that's the question here. So, okay, I thought I changed that. So the solution, we know that modern AI research shows that neither extreme is ideal. Neither extreme is ideal. So a very large model trained on a small data set or a moderately large model trained on a much larger data set. No extreme is ideal. So we then see that a very large model, a very really what's happening here? A very large model, a very large model with with too little, with too little training data, with too little training data cannot fully learn its enormous cannot fully learn its enormous number of parameters. So many parameters remain underutilized, leading to poor generalization. Okay, so that's a large model with too little training. So that will lead to poor generalization. On the other hand, that's conversely, a small model trained on an extremely large data set lacks sufficient capacity to capture complex patterns present in the data. So what do we do? The best strategy is to balance model size, training data, and computational resources, or what is known as compute and computational resources so this principle is known as compute optimal scaling. Compute optimal scaling. Like that. So under a fixed compute budget, so it means you can't get every computational resource you need. Under a fixed compute budget, a moderately large model, trained on a sufficiently large, large, high quality data set typically achieves better performance than an excessively large model trained on limited data. Okay. So what's the verdict? Therefore, the preferred choice is a moderately a moderately large model, trained on a much larger data set, on a much larger data set. So this choice means more efficient use of the available computation. Okay, I think I want to write that too. This choice means more efficient use of the available computation. This choice makes more efficient use of the available computation, improves generalization, and usually results in lower prediction error. Yeah, so with this, we come to the end of this interesting video about why large AI models suddenly become excellent. So again, I'll just show the questions. So here you can see all of questions 1 to 3. I've done one already. Then questions 4 to 6. Questions 7 to 10. 11 to 15. And 16 to 20. Can we see 16 to 20 here? No, not all that yet. So you can see 16 to 19 and a bit of 20, but 16 to 19 all. and then 20. Let me know how helpful this is for you. And if there's something else you let me try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you haven't subscribed, what exactly are you waiting for? Why not go ahead and subscribe right now and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can become a member of this channel by clicking on join. That gives you some special privileges that you find out when you click on join. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.